Hi there, this is Alex from Knowm, and this video will introduce you to the Synapse app on the Memristor Discovery board. So the Synapse app is a fairly complicated app to, understand and to execute. Once you have the principles down and you understand what's going on, it's not too hard, but bear with me, there's some information here. And you're definitely going to have to understand this, otherwise you might become frustrated. This experiment is really all about understanding parasitic capacitances and how it's going to affect your experiment. Now, the Synapse app is a stepping stone to our next app, which is the classifier app. And it's intended to evaluate what we call KT-RAM instructions, or the AHA controller, on synapses. Now, in the classifier app, we'll execute instructions on multiple synapses at a time, and in this app, it's all about executing instructions on individual synapses. We can form these synapses through selection of multiple synapses to add redundancy, both on the board and with the selection of the memristors themselves. So, first thing that we have to do is check out the help menu. And I really mean this, you need to read it because it will save you a lot of frustration. Now, the 2-1 configuration consists of two memristors in series with the same polarity. They form a junction, what we call a Vy, and the voltage of that junction, when a voltage is applied, determines the state of the synapse. Okay, so if, say, M1 here is more conductive than M2, it draws the voltage up, and we say that's a positive synapse. Contrary to that, if M2 is more conductive than M1, it draws the voltage down, and we say it's negative. Now, as voltages are being applied, and this effective voltage divider is evaluating, the memristors themselves are changing depending upon the applied voltage and the pulse type. Now, this could seem kind of complicated, and it is, but what you have to understand is that the Memristor Discovery board, it has some capacitance associated with it. And the Knowm memristors, the self-directed channel memristors, can vary in their conductance from rather high conductances or low resistances all the way to very low conductances or high resistances. Now, when the conductance is very low or if the resistance is very high, then the RC effects start to actually cause problems for you. And that is shown here with this oscilloscope trace. Now, I hooked up an oscilloscope to some of the nodes on Memristor Discovery while I evaluated a synapse in two different states. When the memristors were in a higher conductive or lower resistive state, and whenever they were in a lower conductive or higher resistance state. Now, what you should see and what you want to see is something like what you see here, where VA and VY they really match the shape of the applied pulse. In this case, it's what we call a square smooth pulse. And there's no RC effects. Now, if the resistance is high, what happens is that it takes time for charge to bleed off of this Y node. And whenever the applied pulse on the falling edge goes down, that results in a polarity inversion across one of the memristors. That can cause whatever change you just applied to undo itself. The net effect is sometimes you think that you're driving the state of the memristor up and it really goes down. Now, in reality, the memristors might be behaving exactly as they're intended to behave. But what you observe is something that might be a little more frustrating than that. So you got to understand what regime you're in. Are your memristors in a very high resistance state? If they are, and you want to operate them in that highly resistive state, then you're going to have to operate with longer pulse widths and perhaps use the half sign pulse. this will minimize the RC effects and lead to much more deterministic behavior. Okay, so make sure that you understand the RC effects. And if you have an oscilloscope handy, hook it up to this thing and apply these instructions and actually see what's going on. We can't see that directly with this app because we're monitoring other things, but it would be worth your time and effort really understanding what's going on to see that. Okay, so there's 2 ways to configure the Synapse app. Actually, there's 3 ways, but 2 ways right now until we can get our 2-1 discrete chips packaged. So the first way is to take a single discrete chip and place it in the socket, as you can see here, and to manually wire up one of these 2-1 synapses. Okay, so in this case, we have a jumper here in the first slot on the left, and we have a jumper on the second slot on the right, and we're forming a synapse with the first 2 memristors of the discrete chip. All right, so the input signal is going to come in here. It's going to go across this memristor. We're then going to take a wire and jump from this pin to the Y node, and then from the Y node to this pin, it's going to go across this memristor, across the jumper, and then we have our series resistor here and our jumper configurations as such. Okay, so that's the first way. It's relatively straightforward, but you're going to have to manually wire up the synapse. Now, depending on which memristors that you have used to form the synapse, you're going to have to activate, turn on the appropriate switches. So in this case, we used memristors 1 and 2, so we selected switch 1 and 2 up here. If we used memristors 7 and 8, we would likewise select switches 7 and 8 in order to open up those switches and expose that to the driving circuitry. The other, far more easier way is to use our adapter board. You can get this on the web store, and it consists of 6 dip sockets, and you can plug 2, 4, or 6 discrete memristor chips into the socket in order to form a 8-input 2-1 AHA node. Now, the reason why there are potentially up to 6 chips here is to add redundancy to the synapses. So if you have memristors that are stuck or they don't work, maybe they're stuck high, maybe they're stuck low, maybe one memristor is changing very abruptly and another one takes a little more energy in order to move it, so their adaptation rates are different. As you add more redundancy, all that starts to average out. You can take one synapse that might be bad because, say, the A memristor is bad, and another synapse that might be bad because the B memristor is bad, and whenever you activate them together, suddenly you have one good synapse. Okay, so as you add more redundancy, you get averaging, which helps, and you're able to work around faulty devices. Okay, so this is one consequence of AHA computing. It makes it easy to operate around faults and defects by simply adding redundancy to your spike stream. Now, if that last part didn't make any sense to you, forget about it. Long story short, you just need to get this adapter board, plug it into the headers on your board. You're going to have to remove all those jumpers first. Keep these jumpers here on the right in order to select this shunt, and then take off all the jumpers here that couple the switches to the dip socket, and then plug the adapter board in. Make sure you have at least 2 Knowm discrete memristor chips in the socket there. Okay, so let's put that aside and let me show you the control panel. It's pretty simple. As with some of the other apps, you're going to want to select your pulse type. The default is set to square smooth, but you can change that in the preferences. We can change the pulse width and the pulse amplitude. We can select our instruction here. We can click the start button, which will execute the instruction. We can clear the plot, and we can perform an initialization of the synapse. We can affect the sampling rate 1 second or more, just as in the Pulse app. Okay, so the first thing that we need to do is make sure we have a known series resistor in the right shunt. I'm using a 5 kilo ohm resistor for what I'm about to show you. However, if you want to operate the Synapse with memristors in higher resistance states, you could put in, say, a 15 kilo ohm or maybe up to 30 kilo ohm. Now, if you do that, make sure that your pulse widths are much longer. If you want to operate with much shorter pulse widths, you're going to have to drive the memristors into a much higher conductive state, and that series resistor is going to have to come down, maybe down to, say, 1 kilo ohm. Okay, so I have a 5 kilo ohm resistor shunt. I'm going to select the first memristor. I am going to use, let's say, start with a square smooth wave, set the voltage pulse at, let's say, 1 volt, and it's about 50 microseconds. The FFLV instruction is set. This is the forward float low voltage. This is used to read the state of the synapse without inducing change to the underlying memristors or to minimize the change. We are going to click Start. And what's happening now is that the FFLV instruction was executed, and then now every second FFLV instructions are continually executed in order to measure the state of the memristors and the synapse. So if I had selected, for example, the FF operation here, it would have executed the FF instruction, and then it would continue to execute the FFLV instruction every 1 second or whatever is here in the sample rate. Okay, so what we see is 3 time series. The purple time series is the state of the synapse. It's Vy. And you can see Vy on the right axis over here. The yellow and the blue time series are the calculated conductance or resistance of the memristors. Blue is the A memristor of the synapse, and B is the B memristor of the synapse. Now, if you have more than one synapse selected, then the conductances that are shown and the state is shown is that of the 2 synapses being activated together. Okay, so let me unselect that. So now we have just operating on the synapse 1, and we can see the conductance here. Now, if you don't really think in terms of conductance or Siemens, it's understandable. Most of us have been taught resistances, and in some cases that's much easier to understand. You can click the display resistance, and it'll flip everything for you, so you don't have to do all that in your head, and you can display the resistances. Okay, so what we see here is that the A memristor is about 20 kilo ohms. The B memristor is currently at about 80 kilo ohms. Now the A memristor is higher conductive, okay, so it's going to pull the state up, and consequently we see that Vy here is positive. Okay, there's 0 Vy, this is negative, this is positive, and we're currently evaluating at 0.3. Okay, Vy is going to vary typically between minus 0.5 and positive 0.5. Okay, so first thing we notice is that we actually have pretty high resistances, 20 and 80 kilo ohms, and we can drive the resistance down or increase the conductance. Let's operate the forward float instruction and maybe give it 1.2 volts or so. And let's increase that pulse width, pretty high. Heck, let's just go up to, a millisecond pulse. Okay, so we can stop and start. And when we do that, when it clicks stop, it stops those low voltage reads, and then we hit start again, it executes whatever instruction that we have selected. So what we can see is that after executing that FF operation, the conductance of both of the devices increased, or consequently the resistance decreased. Okay, so we went from 80 kiloohms for memristor B down to about 2 kiloohms. And for memristor A, we went from about 20 kiloohms down to about 10 kiloohms. This is pretty good. We can do it again, and we notice that we're gradually increasing the conductance of the devices. We can just keep hitting this if we'd like, and we can just keep driving that resistance down lower and lower and lower. Now, I would recommend that if you're trying to increase the conductance of the memristors, that you use this FF operation. And there's a fairly good reason for this, which I should probably explain right now as an aside. Okay, an aside for why you want to use the FF operation in order to increase the conductances of your devices. If you recall from previous videos, you got to be careful about applying positive voltages to these memristors and driving them into highly conductive states where they can burn themselves out. Now this gives a little bit of a dilemma when we're trying to increase the conductance of our synapse. Now remember that our 2-1 synapse is formed of 2 memristors in series, and we're applying a voltage, a forward applied voltage, FF, across both devices in series. Okay, now, because of the effects of a voltage divider, let's say memristor A, this memristor, is very conductive. That will make it so that less and less voltage drop occurs across that memristor, more voltage drop across the memristor that has lower conductance, and then that will in turn drive the conductance of that memristor up, and it sort of balances itself out. In other words, it has a self-limiting feature. We call this AntiHebbian learning. So it makes it much, much harder to drive the memristors into highly conductive states because it's self-limiting. Suppose you had 1 volt across both of these memristors in series and that both memristors had the same resistance. That means half of the voltage would be dropped across each one. Okay, well, imagine you had 1/10 of the voltage was dropped across memristor A. It was 10 times more conductive than memristor B. Well, as that becomes more conductive, the voltage drop decreases, and the amount that the memristor is going to further increase its conductance eventually gets shut off because that voltage goes below the threshold of the device. Okay, so it is much safer to use the FF operation in order to drive increased conductance in your synapse. Okay, we're back. So we have initialized our synapse in terms of the memristors, so they're both in higher conductive states. We have our A memristor is in 3.4 kiloohm state, and our B memristor is in about 1.2 kiloohm state. That puts our synaptic output slightly negative. Okay, so right now we have our pulse set to square smooth, 1 volt amplitude, 50 microsecond. You can fiddle with this however much you want. What we're going to do is increment the synaptic state positive. To do that, we're going to use the FFRH, that's forward, float, reverse, high instruction. I will be going through all of these instructions and showing you exactly what they are and what voltages are being applied in a bit. But for now, let's just try to increment the synaptic state positive. Okay, so we're going to click stop here. That will stop the application of the FF low voltage pulses to be reading the state over time, and then we're going to hit start again, and that's going to apply it. Okay, what we've seen is a big jump. We've gone from minus 0.24 in the synaptic state to positive 0.16. Notice that the A memristor, this blue one here, its resistance has maintained. It's the same, and the resistance of the B memristor has increased. Okay, so first thing you should notice is that we have applied a voltage in this instruction across just one of the memristors, across the B memristor, and we have driven it to a higher resistance or lower conductive state. That has caused its resistance to rise above the resistance of the A memristor, and consequently the synaptic state has changed. We can try to drive it back. We can select the FFRL instruction. We're going to stop. That'll stop application of the forward float instruction, and then we can hit start again, and we can drive the state back. Now notice that we did not drive it all the way back to where we started. There is a difference sometimes between going forward and back because we're changing different memristors and they have different adaptation rates. They respond differently to voltages. Every memristor is slightly unique, but we could say hit that again and we could drive it down even more. Now if you want to have finer grained incrementation, you can play around with the applied voltage and the pulse width, keeping in mind the RC effects of your circuit. So if you're trying to reduce the incrementation by, say, reducing the pulse width, but your resistances of the memristors in your synapse is very high, that might not work out for you very well. Okay, so next up is a tour of all of the different instructions. Okay, so we're almost done. Up next and last is a little tour through the instruction set. So first thing you want to do is go to the Help menu and scroll to the bottom where we list all the different instructions that are given here in the control panel. And we have a little diagram here of a differential pair synapse. So we have M1, we also call that the MA, memristor A, and we have M2 or memristor B, and then we have these nodes A, B, and Y. The nodes A, B, and Y match up to the Memristor Discovery board. If you have another analog discovery or an oscilloscope, I'd highly recommend putting some probes on those points and actually checking out the waveforms as you apply instructions. Just set some triggering and execute an instruction and actually see what's going on. There's no substitute for getting your hands dirty and actually taking a close look at the board and all the nitty-gritty details. Okay, so we have three types of instructions. We call them atomic instructions, compound instructions, and conditional compound instructions. Really, all that's going on is that we have these two memristors and we're applying voltage pulses of various polarities and in some cases magnitudes across the A, B, and Y nodes. If we're going to be reading the state of the synapse, we're going to be applying a voltage across both of the memristors in series. And if we're trying to drive feedback of one form or another, we're going to be applying a voltage just across, say, the M1 or just across the M2 device in different polarities. And if you basically make a list of all the different ways you can do that, you'll end up with essentially the instructions we have here. Okay, so let's start off with the atomic instructions, and we'll move our way out through, and then I'll give you a little tour of what it looks like when you actually execute them. Okay, so the FFLV, that stands for forward float low voltage. We're applying a forward applied voltage, which means the negative potential or ground is going to be at B and the positive potential is going to be at A, and we're applying that voltage across both of the devices in series, and we are letting the Y node float. That means we're not applying feedback. So forward float low voltage. The low voltage implies that we're performing a read operation, that we want to minimally disturb the state of the memristor. So in this case, it's hard set in the source code to 0.1 volts. If you want to change that, you better know how to modify the source code. RFLV stands for reverse float low voltage. It's exactly the same thing with the polarities reversed. FF stands for forward float. But in this case, the voltage that applied is whatever you have set here on the amplitude slider. So amp here is in reference to amplitude slider. RF exactly the opposite. The voltage as given by the amplitude slider is applied in reverse across the A-B nodes. The FF operation is very useful for sort of initializing the conductance, as we showed previously. The RL and RH stands for reverse low and reverse high, but note that it just references you to some other instructions, because that is really, there's 4 different ways to affect the state of a differential pair synapse, right? So the state of the synapse is sort of, it's performing a comparison between the conductances of the 2 memristors. And there's 2 ways that you can say drive the state up. You could increase the conductance of the A memristor, or you could decrease the conductance of the B memristor. Okay? So the BDN stands for B down, ADN stands for A down, A up, B up. Okay, up and down is in reference to the conductance, not the resistance. So if you wanted to, say, increase the conductance of the M2 memristor, the B memristor, you're going to want to do the B up, RL B up. So you increase the conductance of the B memristor, you're going to be driving its conductance up, but you're going to be driving the synaptic state down, which is where the RL comes from. R stands for reverse, means the polarity applied is reverse, and L stands for low. You're driving the synaptic state low. Now the reason for these F and R, forward and reverse, has to do with the flip-lock cycle. We're going to cover that in another tutorial. This is about AHA computing. The long story short is that we need instructions that allow us to affect the state of the differential pair of memristors without causing saturation of either device. So if you imagine, if we just applied voltages, sooner or later the conductance of the devices would saturate and synapse would become useless. Likewise, if we reversed the polarity and kept on driving them to very, very low conductances, pretty soon the device states would saturate, the synapse would become useless. And so we're constantly toggling back and forth between forward applied voltages and reverse voltages. We're trying to normalize the conductances. So forward instructions are paired with reverse instructions. This is where we get into the compound instructions. So we have 2 compound instructions here. We have the FFRL and FFRH. So forward float, reverse low. The forward float is applying positive voltages, driving the conductance of the devices up, and the reverse instruction is driving the conductances down. But because we can affect the synaptic state, we can drive it either up or down by either increasing or decreasing the conductance of one or the other memristors. In this case, we picked the RL to represent the driving the conductance down. Now, if you recall our previous discussion about the importance of not driving the memristors to very high conductance states to avoid burnout, this is why. So our feedback instruction, where we're applying the voltage directly across the memristor, we don't want to apply that voltage in the positive going direction because the conductance will increase and we could potentially burn it out. And so whenever we do apply the feedback, we're doing it in the reverse direction and we're driving the conductance down. So it's safe to apply large voltages directly across the memristor so long as you drive the conductance down, because that results in negative feedback, the conductance goes down, the current goes down, and you're not going to blow the thing up. Okay, so the conditional compound instructions. This is where things start to get a little more interesting. We start to get into notions of AHA computing, AntiHebbian and Hebbian computing. The RU stands for reverse unsupervised, and the RA stands for reversed anti-unsupervised. And it's just what this says here. Basically, what you're doing with the reverse unsupervised is that you're measuring the state of the synapse, and then you're applying feedback in such a way as to enhance that state, to drive it further into the state. So if the synapse evaluated positive, then you're going to want to apply an RH instruction, reverse high, in order to make it more positive. And likewise, if evaluated negative, you're going to want to apply an RL instruction in order to make it more negative. Now that's the basics, so I'm going to close out of this, and we're just going to next show you examples of these instructions in action. Okay, so let's select the first synapse. We are using the adapter board rather than configuring the synapse with a discrete chip. You can do either one. If you configure the synapse with the discrete chip and you have the jumpers and whatnot, make sure that you pick the appropriate switches as shown in the help file. Okay, we have our amplitude set to 1 volt, pulse width set to 50 microseconds. This can be whatever you want. Pulse is square smooth by default. No need to change it, but we could if you wanted to. Let's start off by doing an FFLV operation just to see where we start here. So right off the bat, we are reading Synapse 1 is looks like it's pretty well initialized. Let's drive the conductance of the B memristor down. So we're going to pick RH B down. Okay, this is driving the conductance, not the resistance. So let's do that. So the B memristor here, we can see we executed the B down instruction, and as per what we told it to do, it went down. The A memristor held steady. We can try to do that with the A memristor, try to bring that down. So let's stop and start again, see if we have anything there. Okay, so like we did before, this time we applied the A down instruction and we decreased the conductance of the A memristor. Okay, so let's try the FF operation. This is going to apply a voltage across the pair. Now, notice that the conductance of the two devices are about the same. Remember, if you wanted to see it in terms of resistances, we can do that. So we have 23 kiloohms for the A memristor and 6 kiloohms for the B memristor. Let's go back into conductance. And let's lower the voltage here. And then we'll just slowly start to ramp it up. So we're going to start with, say, 0.2 volts. Now, theoretically, when we apply a voltage across both devices in series, 0.2 volts, the voltage drop, let's do 0.1 volts just to be safe here. The voltage is not going to be enough to affect the state to increase the conductance. So let's start again. And notice that we did not make a change. Now we can ramp it up to 0.5 volts and we can do this again. We can see if we make any change. Notice still nothing. Let's put it up at 0.7 and we're just going to be increasing this. Okay, so 0.7. Now notice that we have slightly increased the conductance of the A memristor. And consequently, we've driven the synaptic state a little more positive. Now, why is this? Okay, so if we look at the resistance, we notice that we've decreased the resistance of the A memristor, and the B memristor stayed the same. Why is this? Well, it's because most of the voltage drop occurred across the memristor that had the higher resistance across it, right? Given Ohm's law, you can work out what the voltage drop is going to be across each memristor. The more resistive the device is, the more voltage is going to be dropped. And so when we applied 0.7 volts across both of them, the majority of that 0.7 volt drop occurred across the A memristor because it was more resistive. And it caused it to increase its conductance or decrease its resistance. This is why it is safer to drive the conductance increase of the memristors in the pair via the FF operation. Okay, so it has a automatic self-limiting behavior. Okay, so we can try this again. and see if it's going to drive it at all. We can also press the S key on the keyboard if we want to just hammer this thing. Okay, so I'm hammering it. Notice we're dropping the resistance of A memristor. There we go. And we have dropped it down. Notice that as soon as the A memristor resistance dropped below the value of the B memristor, then the B memristor started to drop. Okay, so we have just hit the pair with this FF operation, and we've driven the conductance down, and they're roughly the same. Now the FF operation is an anti-Hebbian instruction. It means that whenever you apply it, chances are that you're going to affect the state. Whatever the state evaluated at, if the synaptic state was positive, operation of the FF instruction will make it less positive or more negative. And if it was negative, it'll make it more positive. Okay? It's anti-Hebbian. It's the state that is affected by the operation is going to invert. Okay, so we started off, we drove the conductance low, then we drove the conductance high. Now in the background, after every time we hit the start button, it's applying the FF low voltage operation. So now let's check out the FF RL instruction. RL stands for reverse low, low being in reference to the synaptic state, not the memristor. So the application of the FF RL instruction should drive the synaptic state low or negative. Okay, so let's stop that, start again, and we've driven the synaptic state negative. We've gone from 0.06 to minus 0.34. We can try to reverse that with the RH instruction. So we're going to start that, and we're driving it back up. Notice it didn't go all the way back up to where it started. Sometimes the forward and reverse instructions do not have equal magnitude. The devices can be stochastic. This is all stuff that you have to deal with. This is real life. Okay, so we're going to use the keyboard, and we're just going to repeatedly hit it with the RH instruction. Notice we're getting a little bit of incrementation of the synaptic state. It's sort of making its way up. We have some noise here. We have the amplitude set at 0.7. Now if we wanted to hammer this thing, why not? Let's hammer the thing. Okay, let's put a volt across it and execute an instruction. Bam, okay, we got it all the way up. So these devices are voltage dependent, as memristors should be. The bigger the voltage, the bigger the change you can expect. Okay, so we have done most of the instructions here. Let's take a look at the RH, RL, and B down, A up, B down. These are various ways to affect the state of each individual memristor. So let's just take a look. Let's try to say, let's put this into the conductance mode because these instructions are in reference to the conductance, not the resistance. So the A and B memristor right now are about equivalent. Let's try to drive the conductance of the A memristor up. So we're going to see if that works. There we go. So we've driven the conductance of the A memristor up. Let's see if we can follow that with the B memristor, and we're going to try to drive that up. Let's see, what do we have? Nothing. A whole lot of nothing. Oh, there we go. Okay, so it notice that the amount of conductance change, the response of these two memristors is not the same. And this is the case for each individual memristor. Just because you have some model that fits a memristor doesn't mean that that exact same model is going to fit the memristor right next to it. Okay, memristors are, at least these, are built as a function of sort of random faults in the device. Okay, think of it as cracked glass. You know, you're sort of shattering it, and you're forming all these different pathways. And the pathways between each memristor are not the same. And it results in slightly different thresholds. It can result in fairly significant changes in the responsiveness of a device and how many intermediate states it can hold. There's a distribution of memristors that result, even if they're fabricated right next to each other. Okay, so when you design circuits with memristors in mind, you have to design it with the idea that they're not going to have exactly the same reaction to the same voltage pulses, okay, as you can see here. Okay, so I'm going to use the keyboard, and I'm going to keep on hitting the B memristor, and I can keep on driving its conductance up like that. So notice this B memristor is more incremental, had more intermediate states. It was more, the response was less, the conductance change was less per each individual pulse. Whereas the A memristor, that same voltage magnitude drove a much bigger change across it. Okay, so we drove the conductance of each individual one up. Notice as the conductance of the B memristor went up, the synaptic state went down and went from positive to negative. Okay, again, the synaptic state is basically the voltage as given by the voltage divider between the A and B memristor. Finally, we can see if we can drive the conductance back down again. So the A memristor is the blue trace here. So let's see if we can drive that down. And let's see. Oops, I did. The B memristor is the yellow line, and indeed we drove it right back down again. Now let's see if we can follow up with the A memristor, drive its state back down, and we did that as well. Okay, so we gave you a pretty quick tour through the instructions, minus 2, which is getting into more advanced AHA computing. These are the conditional compound instructions, the RU and RA instruction. Okay, so what happens here, it's pretty simple. The device, the synaptic state is read, and if we're going to do the unsupervised, the reverse unsupervised instruction, it's going to apply feedback in such a way as to accentuate the state. Okay, so right now the state is negative. It's reading minus 0.3 volts. So if we pick the FFRU instruction and we execute that, what we should expect is that the state will become more negative. And as you can see here, it did. It went from minus 0.3 to minus 0.34. And as we keep hitting that, we should be driving it further and further into the negative territory. Now, the RA instruction is the opposite, but it doesn't mean that it will drive it positive. What's going to happen is that it will drive it positive so long as the synaptic state remains negative, and as soon as it becomes negative, or sorry, as soon as it becomes positive, it will then drive it negative. Okay, so unsupervised, imagine here's 0, here's positive, here's negative. Unsupervised drives it away from 0, makes positive more positive, it makes negative more negative. Anti-unsupervised takes positive, turns it into negative, or takes negative and turns it into positive. Okay, so we're going to select the anti-unsupervised, and we're going to execute that. Notice it went positive. Now if we execute that again, it's going to drive it right back down. And by executing anti-unsupervised instruction, if the amplitude of the voltage is high, you'll get an oscillator. Okay? Now as we decrease the voltage, you'll start getting more towards 0. It will start honing it in towards 0. And in the case of really well-balanced memristors and the anti-unsupervised instructions, what you'll eventually do is drive that state right to the noise level, and you'll get a random number generator, which is pretty cool. Okay, so that concludes the demonstration of the instruction set for the Synapse experiment. And next up, we're getting fancy. We're going to go to the classifier.